Good evening everyone. I welcome you all to the problem solving session of the NPTEL course on ice engines and gas turbines. I am Pradeev E. I am PhD student. I am one of the TA for this course. So today I have some questions on centrifugal compressors and axial compressors. So we can get started with the questions. So the first question is by considering the expression of turbo machinery equation, which of the following condition is valid for work producing device? The torque of the rotor is equal to mass flow rate of the fluid divided by C. It should be C, mass flow rate into, and it is CW2 R2 minus CW1 R1. So for a work producing device, it is said that CW is the velocity component and R is the radius of the rotor. Suffix 1 and 2 represents inlet and outlet condition. So 1 is inlet and 2 is outlet. So when multiplied with the mass flow rate, this C into CW into R will become CW into R into m dot will represent the change in momentum, or this is directly angular momentum. So now we have angular momentum at the angular momentum is represented by m. We will represent it by m, and we have m2 minus m1, and when the device is producing work, that means the outlet of the angular momentum of the fluid at the outlet will be less than the inlet, right? So for work producing, outlet will be less than m at inlet. So that means the angular momentum is transferred to some shaft, and that is converted as torque, and that is the work that is produced. So now this is angular momentum at the outlet is m2 is less than m1, or we said m dot CW2 R2 is less than m dot CW1 R1. Now m dot cancels. We can divide this expression by m dot, and then we will have CW2 is into R2 is less than CW1 into R1. So answer is B. I hope the problem is clear. If you have questions, you can ask now. In turbo machinery, which of the following option is correct based on the change in kinetic energy due to change in radius of the rotor blades? So reaction effect only, impulse effect only, both impulse effect and reaction effect, or centrifugal effect only. I hope this is visible to you. Can you say if the text is visible in the chat box? some more visible. So maybe it is better now. Yeah, okay. So in turbo machinery, which of the following option is correct based on change in kinetic energy due to change in radius of the rotor blades? Can someone answer this? Yes, option D is right. Because for a centrifugal compressor we will have the blades, we will have an axial inlet and then we will have a radial outlet. Because of the movement of the blade, then we impart a centrifugal force uh, on the fluid, and then we get higher velocity, and then we will convert the velocity to pressure, and then that's how we increase the pressure of the fluid. So which of the following compressor is much suitable for low volume flow rate? Centrifugal compressor, axial flow compressor, both centrifugal and axial flow, none of the above. Yes, option A is right, because centrifugal compressor is generally suitable for low volume flow rate, and it is also much efficient for low volume flow rate. When the volume flow rate goes high, then it is advisable to axial flow compressors, where the efficiency is better for high flow rate, high flow volume. So axial. So in centrifugal compressors with aluminum mains, the stage pressure rise is approximately dash of its initial pressure for a stage. Two times, 8 times, 3 times, 6 times. So answer is 4 times. So that means the P02 by P01 for a single stage centrifugal compressor is generally 4:1. Next question, in centrifugal compressors, which of the following component is mainly used to avoid the flow between the high pressure side to low pressure side? Ported shroud, stator, impeller, or volute? So ported shroud is correct, because it will not allow the fluid to flow from the high pressure side to low pressure side. So in case of centrifugal compressor, the high velocity of air is decelerates in blade passages provided by diffuser, impeller, stator, or all of the above. So the high velocity of the air, in centrifugal compressor, the rotor or the impeller will impart the velocity, right? So rotor or impeller will impart velocity in the to the fluid, and pressure is increased by using a diffuser, a stator, right? Stator is used to convert velocity energy to pressure energy. For centrifugal compressor, the friction loss in impeller and diffuser leads to static pressure loss, static temperature loss, stagnation pressure loss, or stagnation temperature loss. See, yes, it will lead to stagnation pressure loss. If you draw the TS diagram, then you will be knowing. So ideally we will compress from 1 to 2. Now say for the same thing, because of the friction you will reach somewhere at this point. In centrifugal compressor, inducer is a part of diffuser, stator, volute, or impeller. Yeah, inducer is a part of impeller. For centrifugal compressor, without inlet guide vanes, the flow enters into impeller eye axially or radially, both axially and radially, you can't say. So here C represents absolute velocity, CA represents axial velocity component, suffix 1 represents the inlet impeller. Yeah, option A is correct, because for a centrifugal compressor we have the impeller eye, and we assume the fluid enter axially, and we can assume C1 is equal to CA1. The total velocity is, there is no radial component, this component doesn't exist, so, and there is only radial component, axial component. By considering the centrifugal compressor, please choose the following correct option. Beta 2 is 90, represents backward vanes or radial vanes, and beta 2 less than 90, which represent forward vanes or backward vanes or radial vanes, and beta 2 greater than 90 represents radial, backward, or forward vanes. option C is right. When beta 2 is 90, it means radial, there is no axial component. And then beta 2 less than 90 degrees for backward wind, and beta 2 greater than 90 is represents forward winds. In general, the backward and radial vanes are preferred in centrifugal compressors respectively due to less work input and easy to fabricate, high pressurized and difficult to fabricate, high work input and easy to fabricate, low pressurized and easy to fabricate. Yeah, option is A. It is backward vanes are has less work input, but radial vanes have are easy to fabricate. Choose the correct expression of work done of centrifugal compressor without inlet swell as well as unit slip factor. Work done is equal to blade velocity multiplied by well component at inlet, or absolute component at outlet, or radial component at inlet, or well velocity component at outlet. Yeah, it is work done is blade velocity into well velocity component at outlet, because we have seen that work done is equal to blade velocity into CW 2 minus CW1, and here CW2 we have CW1 is 0 because it said there is no without inlet swell, so there is only the well component at the outlet. For a centrifugal compressor, which of the following component is responsible for decreasing the temperature and increasing the entropy respectively? Accelerating nozzle and inlet guide vanes, impeller, diffuser, or volute. Yes, accelerated nozzle and inlet guide vanes are responsible for decreasing the temperature and increasing entropy. For the given expression of flow coefficient of centrifugal compressor, identify the right option for alphabet X. Flow coefficient is absolute velocity by blade velocity, or radial velocity, relative velocity, constant. So I think this would be covered in the theory part. I have noted down it as radial velocity by blade velocity. Okay. Now these are about the centrifugal compressor questions. Now we will move on to axial flow compressors. For flow through an axial flow compressor stage, as given in the following figure, which parameter do curve 1, curve 2 and curve 3 represent? So there is a rotor till this point. So during the rotor all the three curves are increasing, and during the passage all three values are constant, and then at the stator state, curve 1 increases, curve 2 is flat, curve 3 is decreasing. So now curve 1 could represent static pressure or stagnation pressure. These are the options there. And curve 2 might represent static temperature or stagnation temperature, and curve 3 can represent tangential velocity, absolute velocity. Yep, these two. Yes, option D is right. In the So static pressure will increase in the rotor, and stagnation temperature will remain constant, and then tangential velocity keeps decreasing. I think so. The first curve, static pressure increases during rotor state and then remains constant, and then again during stator it increases. So how it increases here? Because the stator will reduce the velocity and increase the pressure, right? And then for the curve 2 represents stagnation temperature. So stagnation temperature also increases at rotor state and then remains constant, and then during stator it will also remain constant, because only the pressure is converted to thermal component, temperature component. And for the tangential velocity, it initially increases and then remains constant, and then during the stator, where the velocity head is converted to the pressure head, the velocity decreases. So next question, which of the following is correct correlation between the blade loading coefficient and flow coefficient for an axial flow turbine? Here alpha is absolute velocity angle, beta is relative velocity blade angle, suffix 2 and 3 represents inlet and outlet condition for rotor. So blade coefficient is 2 into flow coefficient into tan alpha minus tan alpha 2 minus alpha 3, or tan alpha 2 plus tan alpha 3, or tan beta 2 plus tan beta 3. So blade loading coefficient is D is the right answer. In thermodynamic analysis of flow through an axial flow compressor, which of the following statement is correct for the rotor? So for the rotor, where we impart work done, where we impart mechanical energy into the fluid, stagnation temperature remains constant, static temperature increases, or stagnation temperature increases, both stagnation and static temperature increases. So when it comes across the rotor, uh, both stagnation and static temperature increases. For flow through axial flow turbine, stagnation temperature across the nozzle decreases or increases, remain constant, none of the above. Yes, remains constant is correct, because through a nozzle there is no external work done and there is no enthalpy added to the fluid, so that means then the stagnation temperature will be the constant. Maybe you can write like this, H01 stagnation enthalpy equal to H02. So this is Cp T01 equal to Cp T02, and only the H plus C1 square by 2 Cp, so H2 plus C2 square by 2 Cp. Here C2 will be greater than C1 for nozzle. H1 will be greater than H2. For axial flow compressor, which of the following assumption is for free vortex condition? Static equilibrium, difference between nozzle and stator. Okay, sorry. I think you are not able to unmute. Okay, fine. Across a nozzle, in both nozzle and stator, this is the same. The stagnation conditions remains the same. In stator, that is used in compressors, is used to increase the pressure. So for compressor, the objective is to increase the pressure, right? Just come back. So compressor, increase pressure. So pressure cannot be directly increased by any means. So first we will have a rotor, and this rotor increase velocity, and then you convert this velocity to pressure using a diffuser or a stator. So in stator, the velocity head is converted to pressure head. Okay, so across the stator you will see the velocity will drop, and pressure will go ahead, because that is what needed for a compressor. Whereas nozzle is used for condition in cases like where we want propulsion at the outlet of the jet engines, where we want a high jet velocity of the exhaust gas. Then we will convert the pressure head to the velocity head, and then we have the exhaust jet coming out. So nozzle objective is to increase velocity, and so it does by converting pressure head to velocity head. I hope this is clear. Okay, thank you. Now for axial flow compressor, which of the following is assumption for free vortex condition? Static equilibrium, dynamic equilibrium, radial equilibrium, or chemical equilibrium? I think this is some part of the theory, and the answer is radial equilibrium. Which of the option is correct for flow across the rotor of axial flow? Flow across rotor of the axial flow turbine. Yes. So here absolute velocity increases, relative velocity component decreases, axial velocity remains constant, all of the above. So answer is axial velocity remains constant. It seems like these two are right. Absolute velocity. So it should be all of the above. So next we have a problem. Okay, the impeller of a centrifugal compressor rotates at 20,000 rpm. N is equal to 20,000 rpm, and the compressor delivers air at volume flow rate of 20 meter cube per second. Q is 20 meter cube per second, with a pressure ratio of 4:1. So PR pressure ratio is 4:1. The isentropic efficiency of the compressor is 90%. Eta C is 0.9. The axial velocity of the flow is 80 meter per second. So CA1 is equal to 80 meter per second, and it is constant rho. The outer radius of the impeller, which has radial blades, is twice the inner one, and neglect the slip coefficient. Assume that the ambient air conditions are 1 bar and 303 Kelvin. First is to find the blade speed at the impeller exit. So first we can so this can be set as P03 by P01, and P03 by P01 can be written as 1 plus eta C U2 square, or here 1 square, divided by Cp into T01, the whole power gamma by gamma minus 1. So here we know that this is the pressure ratio, which is 4:1. Eta C is known. U can be calculated. U has to be calculated from here, and T01 we can calculate with the given details. So T01 is equal to T1 plus C1 square by 2 Cp. So T1 is 303 Kelvin plus C1 square is 80 square by 2 into 1005. So what is T01? Can you calculate the stagnation temperature? Yeah, it is 306.18 Kelvin. Now we know that putting this expression, we have 4 is equal to 1 plus 0.9 into U square divided by Cp is 1005 into T01 is 306.18. The whole power gamma is 1.4 by gamma minus 1 is 0.4. Now we have to find the U, value of U. So now I can write okay, u square so now I can write 1 plus 0.9 into u square divided by 1005 into 306.18 is equal to 4 power 0.4 by 1.4. Now 0.9 u square by 1005 into 306.18 is equal to 4 power 0.4 by 1.4 minus 1. U is equal to maybe first we can compute this alone. Okay, so it is 0.48. Now u square is equal to 0.48 into 1005 into 306.18 divided by 0.9. U is square root of this value, 0.48 into 1005 306.18. Can you compute the value of u? 407.62 407.62 meter per second. So now blade speed of the impeller is 405. So this is the closest one. So for blade load, actually I don't know much about this blade loading coefficient. I haven't gone through the videos fully. I will take up this question. I will check in the class and I will let you know. Blade loading coefficient for centrifugal and axial compressors. Meanwhile, you can also put in that discussion forum. I hope you know about it. Anyway, I will do this, but I just want to let you know. Okay, so blade tip velocity we have found. Now the power required for the power required for the drive, power required to drive the compressor. So that work done so work done per mass of the fluid is we have u2 CW2 minus U1 CW1. So here it was said that the inlet is there is only axial velocity, so we can neglect this term, and we have U2 and CW2 are same because it is said we can assume. Okay, for ideal case these two are same. The slip coefficient or slip, nothing is told about the slip, so neglect the slip factor, yes. So then we assume these two are same, and then that is equal to the 407.62 the whole square. So this is the work done per mass. Topic like centimeter difficult to understand, so would you give me tips for this issue? Tips in the sense,
Sir, good evening, sir.
Maybe after this problem I will open the previous last week's class notes, and somewhere I have drawn the velocity triangle, so I can go into that and I can explain you how it works. Okay, can you compute this? One 166.54 yeah. Now we want to calculate the power. Power will be work done for unit mass into mass flow rate, and so far we have only Q, that is 20 meter cube per second. 20 meter cube per second. So we need to calculate the density and then get the mass flow rate and then put into the power equation. So for density we have P by RT. The value of P is 1 bar, and 1 bar is 1 into 10 power 5 pascals, and R is 287 into temperature is 303. So can you compute the value of the density? .149 kilogram per meter cube. So to get the mass flow rate, we multiply rho by density. So we have 1.149 into 20. So what is the mass flow rate? So this is 23 kilograms per second. Now power will be 166.154.06 into 23. Can you compute the power? Is it 382? So this comes to be 3.8. But there is no option for this here. Has anyone found where we went wrong? Okay, this anyway I will try to figure it out in the, and maybe I will correct this and upload in the PDF. Next question. Inlet and outlet diameters of the impeller in meters respectively. So they said the outer radius of the impeller is twice the inner one. Okay. So that means d is 2 times the small d, and the d can be, so we have velocity that is 407 meter per second, so that should be equal to pi d n by 60. Now substituting the known parameters, that is 407, we will calculate d. D is 407 into 60 divided by pi n, that is 407 into 60 by 20,000 into pi. What do we get for the value of d? Yeah, 0.38 meters, and small d is capital D by 2, that is 0.38 by 2, we get 0.19 meters. So the inlet diameter is 0.19, outlet diameter is 0.38. For the next we have width of the rotor blade at the inlet in meters. So this flow rate is C1 into cross-sectional area, right, and flow rate Q is known, so this is Q, and Q is 20 meter cube per second into C1 is 80 meter per second, and area is pi d1 into b1, and d1, and d is known, so calculating b1 we will have 20 by 80 pi into d1. d1 is 0.19, and then you can calculate b1. 41 meters. Okay, now since someone asked for the velocity triangle, or I think it's better that I prepare well for the velocity triangle and come back. Maybe in the next class I will start with the velocity triangles. It is good that you ask me questions and keep me engaged. Actually, I was expecting this from you from the very beginning. Now I have noted one question on blade loading coefficient for centrifugal and axial compressors, and next one is about the velocity triangle for both centrifugal and axial compressors. So next class, in the next week I will start with this first. Next question. Single stage axial flow compressor caters a small pressure rise because it experiences adverse pressure gradient, favorable pressure gradient, blade failure due to high impact flow, or low blade height. Yeah, because it experiences adverse pressure gradient. In axial flow compressor, the blade are facing the stalling condition due to large incidence angle of the flow, variation in mass flow rates, variation in rotational speed, or all of the above. Large incidence incidence angle will also cause the stalling, but it can also be caused by variation in mass flow rate and variation in rotation speed. So all of the above. In thermodynamic analysis of an actual axial flow compressor, the stagnation temperature of stator remains constant because no work interaction across stator, very less work interaction across stator, very large work interaction, or stator plates are movable. Yeah, option A is right because there is no work interaction across the stator. Only rotor will have work interaction, and stagnation temperature will increase across the rotor. Across the stator. So this is the TS diagram, and we are asked to find the zone A. So zone A is ideal work input or actual work input, or losses during work input to the compressor, or losses in the presence of rotor. zone A is from this to this, that is from T03, from T01 to T03. Yeah, actual work input is right, because T01 to T02 it has taken a curved path, this curved path, right, which represents the increase in entropy, which is an actual case. And here, as we see, this one represents the ideal work input, that is T03 minus T01. This will represent ideal work input. For axial flow compressor, the work input to the compressor is small theoretically if compression process is isentropic or adiabatic or isothermal or isobaric. A is correct. For isentropic we will have delta S equal to 0. There is no increase in entropy. For adiabatic it means Q is 0. For isothermal temperature is 0. Isobaric is not at all possible for a compressor, that is there is no pressure rise. For all conditions you can write the expression, thermodynamic expression, and you can see the work done. Flow through the stage of an axial flow compressor, which of the following is correct regarding the absolute velocity? So this is absolute velocity. Maybe you cannot see it. So in the first case, it increases, probably this is the rotor and the last region is the stator, and intermediate there is a constant gap. So in the first case it is increasing and then constant for a while and then increasing. So I will also number this. This is A, B, C, D. And in case of B, it is increasing steeply initially and then increases at a less rate in the second stage, and at third stage it again increases. In case of C, it increases, remains constant and comes down, the value goes down. In case of D, it increases initially and then remains constant throughout. So which of the following will represent an absolute velocity? So C is correct. The absolute velocity initially increases because of the rotor, right? And then there is a gap between the rotor, stator, and there is a gap. So during the rotor it increases and the gap it remains constant, and then if the stator, the pressure head is converted back to, the velocity head is converted back to pressure head, so it decreases, right? So this represents the absolute velocity. Can someone say what this D represents? So at the rotor phase it increases and then remains constant throughout. Okay, yeah, D represents, say, stagnation conditions, like stagnation temperature or stagnation pressure. So during the rotor phase, where you impart mechanical energy to the fluid, the enthalpy increases, and then stagnation temperature and pressure increases, and then in the gap it remains constant, and then again in the stator phase also the stagnation parameters remains the same. From the figure of the flow through the stage of axial flow compressor, choose the correct option for section BC. So this BC is stagnation pressure or stagnation temperature for stator section only, or all of the above. Yes, all of the above is right. So this BC represents stator section, and BC is also like it is constant throughout the stagnation pressure, for stagnation pressure or stagnation temperature at the stator phase. From the velocity triangles of an axial flow compressor at the inlet and outlet, identify the right option. Axial and blade velocities are constant, axial and absolute velocities are constant, well and relative velocities are constant, or absolute and relative velocities are constant. Yeah, I think it is simple. So we know that the blade velocity is constant, and axial component is also constant in an axial compressor. For axial flow compressor, blade height continuously decreases or increases or remains constant toward the downstream of flow. See, yes, continuously decreases because the pressure is increasing. So that means the density will increase, and increase in density will say that the volume occupied will be less, and you can assume for a mass where it is constant throughout the compressor at steady state, and because of this, as it keeps on going for different upcoming stages, the blade height can be decreased, and the total cross section area will also decrease. So in case of axial flow compressor, the mean value of work done factor is dash as per the increasing number of stages. Continuously decreases, remains constant, continuously increases. Yeah, it continuously decreases. In case of axial flow compressor, the mean value of work done, I think this is under free vortex condition, degree of reaction for an axial flow compressor is dash to the blade height, directly proportional, inversely proportional, remains constant. So this remains constant. For velocity triangle of a rotor of axial flow turbine, which of the following component of velocity is decreases from inlet to outlet? Axial velocity, absolute velocity, will velocity, both absolute and will velocity. So both absolute velocity and will velocity decreases from inlet to outlet. Choose the correct option for degree of reaction of axial flow turbine, where phi represents the flow coefficient, beta 1 is inlet blade angle of the nozzle, beta 2 is inlet blade angle of the rotor, beta 3 is the outlet blade angle of the rotor, and R is degree of reaction. So A is the correct answer. In case of axial flow turbine with constant nozzle angle condition, which of the following option is correct for A? Yes, outlet nozzle is correct. Okay, I do not have any more questions. So if you have any other questions, I can answer now. If you have questions, you can ask now. I will try to get the velocity diagram if possible now. Okay, I see a question: which turbine produces more work output, axial or radial? Mm, I think it will depend upon the mass flow rate and the pressure ratio and many other parameters. You cannot directly say like axial or. So this is the for the centrifugal compressor. And this is for the axial compressor. Um, okay, so now this is the centrifugal compressor. You can see the blades here, right? These are the blades of the centrifugal compressor. Now the so this is the I root, and then the inlet will be till this in this region. Maybe I will put a different color. So this is the I tip, and inlet can occur in this region. How inlet will be? It will be axial, and it will be perpendicular to the screen. Okay, and for that we have the this velocity diagram here. So we have an inlet velocity represented by c1, and this is fully axial. There is no radial component in it, and this blade is moving towards the right or the clockwise direction. So if you look at a point here on the above the center, then that means the blade will be moving towards the right, and that is represented here, UE. And now this because of these two velocities, we will have something called V1, that is a relative velocity of the air coming in. How this relative velocity comes is like when you from an stationary observer, we see both the velocities going, right? When you are on the top of this, or when you are looking at the center, you can see that velocity of the air going radially away from you, and then you can also see the blade that is crossing from left to right, and crossing the left to right. So that is represented by UE, and the velocity of the fluid that is going axially away from you is C1. Now if you take V1, that is when you are sitting in the when the observer is on the blade, then it will see something some air coming in, right? And that will not be axial, because the assume that C1 is say assume C1 is 5 meter per second, right? And then UE is very high, assuming say it is 50 meter per second. Then UE, that is the blade is moving at a very high speed, but the air coming in is at very low speed. So when an observer is on the blade, it will see that there is a slight the air coming in is not axial anymore. It will come at an angle, right? And that is called as U1, and that is called as a relative velocity. And this angle is called alpha. I hope this explanation is clear. Can Subham is still there? I think Subham has left. Oh, okay. Anyway, if you can understand this, please let me know. Steve, maybe you have understood this earlier also. Yeah, okay. And then at the outlet you have this C2, mark with this one, C2, CR2 and U. Again this U represents the blade velocity. It will be same as this inlet region, or maybe because the radius is different, the omega will be the same, but because of the radius there will be different U value at the inlet and the outlet. So at inlet Ui will be omega into Ri, radius of the inlet, and U outlet will be omega into R outlet. So because of this, that U value will be different from the inlet, and the fluid will be coming, will not come radially, but it will come at an angle, that is marked by C2, and then we can calculate the radial component CR2, and then with this exerts an angle, and that is and there will be some angle. I think at different textbook you can find the different angle. Here I don't know what is mentioned in this book. And so now C2 will also have a radial component and then well component. So this well component is CW2, right? And here it is taken CW2 is U, but here they say CW2 is less than U because of the slip. So that is how you define slip. I think it's slip factor. I hope this velocity triangle for centrifugal compressor is understood. And we go to axial compressor. So axially, here again at the inlet there is a velocity component C1, which comes at an angle alpha 1 when compared to the axial axis, and these are the rotors which is moving towards the right at velocity u. Now this C1 when writing in the velocity, when put in the velocity triangle, will have an axial component CA1, and there is a will component, that is the radial component C, that is called as will component CW1. And this blade, these rotors, I hope you will be able to realize that this axial compressor is like this, and then there are blades, and each blade is represented here, and it is looked at from this angle. So at this angle you will see this blades moving downward or at different sides. So maybe you look from here or look from here, the blades are moving towards the right. Maybe if the rotation is this way, then you will see the blades moving towards the right. That is mentioned here. Now here this is the blade velocity, and again when for a stationary observer you can observe the velocity u towards the right, and the velocity of the fluid coming from top at this point to this point at an angle. So for a stationary observer you can see all this, but for an observer on the rotor, the rotor will also keep moving towards the right, the blade also is moving right, and it will see some fluid coming towards it, but by the time by the time the fluid comes, the blade would have moved a lot. So for an observer at the blade, it will see that the fluid is going towards its left. So that is why we have the this relative velocity towards the left. But when the fluid, this C1 has a well velocity very much higher than the U, but that is not possible, then it will see that the U1 will be on the right side. And similarly you can also tell for this. So the velocity at the outlet of the rotor is going towards the right, C2, incident in an angle alpha 2 with respect to the axis, and this will have an axial component CA2 and then a will component CW2, and from the blade the relative velocity will be V2. Since this velocity has increased a lot and moving towards the right a lot, this component has become lesser. The V2's will component has become lesser. I hope this explanation is clear. Then, are there any other questions? So maybe we can discuss about the blade loading factor. Can you tell what is blade loading factor? Maybe I will not be able to give an explanation now, but we will see and understand it. Yeah. What is blade loading factor? It is loading coefficient. Or if you have any other questions, we can discuss that. Steve Leo, we discussed last time that you are from that college from Coimbatore, right? Kumaraguru. Do you have any other questions? how blade loading affects what? Affects structural performance, or I haven't gone through the blade loading at all. What is blade loading? Okay. I'm also not sure. You can check on the internet. Okay, how much work is given by one blade, so that if the work is high, then it has to undergo a lot of stress. Anyway, I will get this as a gross weight of work to the total area. Anyway, I will find more about it and I will explain in the next class. Is there anything other than plate loading? You have any other questions? No. Okay. Okay, then we can close the session. Thank you for participating. Surely I will get this clarified in the next class about the blade loading. Thank you.